Cerebras Systems and G42 recently announced they broke ground on the largest artificial intelligence supercomputer in the world in Dallas, Texas, dubbed the Condor Galaxy 3. Cerebras of Sunnyvale, California, also home to Apple, is a pioneer in accelerating generative AI, providing the biggest and fastest AI chips in the industry. G42, an Abu Dhabi-based global leader in AI capabilities, together with partners from around the world, are creating infrastructure to accelerate science in molecular biology, space exploration, and many other advanced applications. G42 sees itself as a force for good, seeking to accelerate progress and tackle society's most pressing problems. It's no surprise that Microsoft wanted to get in on that action. Microsoft will invest $1.5 billion for a minority stake in G42, and Microsoft President Brad Smith will take a seat on its board. Microsoft says the partnership will allow the companies to co-innovate and deliver advanced AI solutions for various industries and markets in the Middle East, Central Asia, and Africa. With the breadth of the Microsoft Cloud and its differentiated AI capabilities, the deal significantly advances G42's strategy of delivering generative AI and next-generation infrastructure and services for a range of customers across financial services, healthcare, energy, government, and education, Microsoft said. G42 will migrate its essential technology infrastructure and data platform to Microsoft Azure to benefit from the platform's performance, scalability, and security capabilities, and achieve faster delivery times for customers globally. Condor Galaxy 3 is the third cluster to be deployed in a constellation of AI supercomputers. The Condor Galaxy 3 is twice as powerful as each of the two previous clusters, featuring 64 CS3 systems that are powered by the industry's largest and fastest AI chips, called the Wafer Scale Engine 3, which is a game-changing innovation. The newest cluster will use a staggering 58 million AI-optimized cores to deliver an astounding 8 exaflops of AI performance. What's an exaflop? Picture this. You're a cosmic traveler exploring the Milky Way galaxy, and you've been tasked with counting all the stars in it. Current estimates suggest that our galaxy contains about 100 to 400 billion stars. That's a huge number. But let's assume that there are precisely 250 billion stars for this thought experiment. Now, imagine you have an advanced spacecraft that can visit and count one star every second. If you were to embark on this stellar census, it would take you almost 8,000 years to count all the stars in the Milky Way. That's longer than the entire span of recorded human history. However, if you had an exaflop computer at your disposal, it could count all the stars in the Milky Way in just 1/4 of a millisecond. That's faster than the time it takes for a beam of light to travel the length of a football field. But why stop at just one galaxy? Let's say you wanted to count all the stars in the observable universe, which is estimated to contain about 1 billion trillion stars. With your trusty spacecraft, it would take you an astonishing 31.7 billion years to visit and count each star. That's more than twice the age of the universe itself. In contrast, an exaflop computer could breeze through this cosmic census in a mere 16 minutes and 40 seconds. That's less time than it takes to watch an episode of your favorite sitcom. These speeds are so incredible that it can tackle astronomical tasks, pun intended, in mere seconds or minutes, while it would take humans or less powerful machines thousands, millions, or even billions of years to complete. At the heart of the CS3 is the compute core, an enhanced version of the previous generation WSE2 core. The CS3 core delivers twice the performance of its predecessor. It also features new instructions to speed up nonlinear functions and an improved local cache. A single CS3 has 4 trillion transistors and delivers petaflops of compute, the performance of an HPC cluster in a single device. One CS3 has 44 gigabytes of on-chip memory, which is 880 times more than NVIDIA's H100. Perhaps the most impressive aspect of the CS3 is its wafer-scale integration. Cerebras tiles out 10,000 cores into a single die, and then replicates 84 of these dies across an entire wafer. The result is a single colossal chip, housing an astonishing 900,000 cores, all seamlessly connected by high-bandwidth, power-efficient interconnects. This feat of engineering is made possible by Cerebras' pioneering uniform tile and fabric architecture. The CS3 system, purpose-built for wafer-scale computing, enables large-scale AI model training on a single chip. This means that models like the 70 billion parameter Llama can be fine-tuned in a mere 24 hours. However, Cerebras went beyond just one CS3 and clustered them together to operate as a single unified ML accelerator. By disaggregating compute and memory, the entire cluster functions as a single device, delivering up to an awe-inspiring 256 exaflops of AI compute power, or a quarter of a zettaflop. In a traditional server, the CPUs or GPUs are directly connected to the RAM on the same motherboard. This tight coupling of compute and memory limits the scalability and flexibility of the system. If you need more memory, you often need to add more servers, even if you don't require additional processing power. By disaggregating, these resources can be deployed and scaled independently, leading to better resource utilization and cost efficiency. This is achieved by connecting compute and memory units over a high-speed network fabric, allowing any compute node to access any memory node as needed. The memory capacity of the CS3 cluster is equally impressive, supporting up to 1.2 petabytes of memory. This allows the training of models with 720 billion parameters with 64 CS3 systems up to an astounding 24 trillion parameters at full capacity. Cerebras achieves this through a hybrid storage approach, combining high-performance DDR5 DRAM with cost-effective flash memory. The cluster's interconnect has also been significantly upgraded, now featuring 400 and 800 gigabit links, resulting in an aggregate bandwidth of 10 petabits per second. One of the most remarkable aspects of the CS3 cluster is its seamless user experience. Whether working with a single CS3 system or a cluster of 2,000 of them, it's always presented as a single device, which avoids the complexity of parallel programming for distributed computing. Models of any size can be accommodated, and the scaling remains linear regardless of the scale. This ease of use was exemplified by G42's successful training of a 30 billion parameter model on the Condor Galaxy 1 cluster. In just 5 years, beginning with BERT up through today's GPT-4, the amount of compute needed to train a state-of-the-art model has increased by 40,000 times. As the demands of AI continue to grow at such an unsustainable rate, Cerebras believes that sparsity holds the key to addressing this challenge. By leveraging the inherent sparsity in neural networks and the ability to induce sparsity in dense layers, the CS3 can accelerate all forms of sparsity, leading to substantial reductions in the computational resources required for training. The Cerebras CS3 represents a significant milestone in the evolution of AI computing. Through its innovative architecture and wafer-scale integration, Cerebras has created a system that delivers unrivaled performance, scalability, and ease of use. As the AI landscape continues to evolve, I believe the CS3 will play an important role in powering the next generation of models and applications. Let's take a look at an example of what some researchers are working on with Cerebras technology. This real-time computational fluid dynamic simulation was performed on a single Cerebras CS2 system wafer-scale engine within the NeoCortex system at the Pittsburgh Supercomputing Center. The simulation was made up of 200 million cells, with blue convection structures shown falling from the cold surface, while orange structures rise from the warm surface. This mesmerizing and visually stunning process is driven by buoyancy differences between the hot and cold liquids, and happens spontaneously in a gravitational field. What stood out to the researchers was the new ability to run these calculations at near real time. What you're seeing is approximately the actual solution speed, simulating flows at high resolution. With this kind of power, researchers can do more experiments and achieve better science, dramatically accelerating the design process for solutions like carbon sequestration and blue hydrogen production that aim to mitigate climate change and enable a secure energy future. A simulator like this can be used to predict problems and suggest improvements, leading to faster optimization, reduced costs, and more certainty about a project's viability in the real world. In this video, we looked at the Condor Galaxy 3, an 8 exaflop AI supercomputer from Cerebras, the largest and fastest in the world, installed in Dallas and coming online by June. We looked at Cerebras' design approach of packing 84 die onto a single massive silicon wafer, with on-chip interconnects to achieve the highest performance fabric at the lowest power. We showed how this technology overcomes the complexity of training models on distributed compute over thousands of GPUs by using chips big enough to hold the entire problem. And we talked about how the CS3 cluster presents as a single ML accelerator with disaggregated cluster-level memory and cluster-level compute. This allows for models with up to 24 trillion parameters to be trained on the CS3 in record time without writing any parallel computing code. What do you think about Microsoft's big investment in AI supercomputing and its partnership with G42? How about Cerebras' innovation on wafer-scale chips and model training capability? Do these advancements worry you or excite you? Let me know in the comments. I'd love to hear your thoughts. And if you like this kind of content and don't want to miss out on any important advances, don't forget to like and subscribe. I'm Scott Ingram, and thanks for watching.